So last time we were discussing that every access to a memory cell, we are going to assume it takes one unit time. So now, if we are looking at, if we are looking at, these are most common functions that we will see. So constant function, which is shown as one, so it is not actually one. It might be any time. It might be a fixed time, but the time is going to remain same. So it doesn't depend on input size, and that is what we are going to call it as a constant time. And in terms of time complexity, it is also shown as big O of 1. So we will see the notation in more detail in the next class. But right now, 1 is not one unit time, but some function which is increasing constantly. So it doesn't really depend upon what is my size of n. Then some functions will grow in logarithm manner. So for example, if you are talking about binary search, so whatever is your input size, it is going to take, or it is going to break that input n by 2 in the next step, again n by 2 in the next step, and so on till we find that number. So if you look at input size n, the units it's going to take will be in terms of log n. Then similarly, we discussed some algorithm. If you remember the comparison of A1, A2, A3, we discussed last time. So here, if we actually plotted the graph, so I believe A2 or A1 was in linear time, where as much as my input size, my time is also increasing in a similar fashion. So here, these 7 are the most important functions. So we will see that when we will see some examples and how you can notice that the function is n square, how you will notice that the time complexity is n cube or 2 raised to n and so on. So these are most common functions that we will see. Now we will see some examples. So this I'm going to write. These are just for reference. We will start with some new functions to show all the 7 types of commonly occurring functions. So if you look at, let's say we have, now I'm going to have a very simple program which is just going to print hello. So you might have programs in arranged in different ways, or sometimes we will just see looking at the algorithm how you are going to find out how many times anything is printed. So for now, just we are going to find the running time, kind of a time complexity. So assuming that it is only going to print hi. So let's say the name of the function is hi, and inside we are going to define some integer I, and we are going to write for I is equal to 1 up to I is less than equal to 10, I plus plus. And for this loop, we are going to print. So the syntax is similar to C, doesn't matter much. We are just going to find out how many times the program runs. So starting from a very simple program, which is going to print hi. Now, how many times hi will be printed here? 10 times. So does it matter? So let's say n, I have some n, and we have not defined any input size. But whatever my input size is, really we are not using it, the n here. So every time, even if I, let's say input size is 10, or input size is 100 or 1000, it really doesn't matter, because every time the for loop is still going to run 10 times. So this kind of an algorithm or a program, I just showed the programmatic representation. Every time it is still going to run same 10 times. So this is called as a constant time. So this has a constant time complexity because it does not depend on n. Whatever is your input size, it doesn't depend. And this is in terms of complexity, this type of functions are shown as O of 1. So 1 doesn't mean unit time. 1 here means that it is going to be constant and it is not going to change even if my n, whatever value my n holds, because n is not getting used anywhere. Now, if we replace the same function, just the 10 is replaced by n. So again, the same function I'm going to write. But now instead of saying that print 10 times, I'm going to use a for loop. So you can take n from user, or you can, let's say, so how many times hi is going to get printed in this case? 100 times. So most likely this n, we are not going to have it fixed. We are going to get it as input from user. So let's say again here you're taking print by asking user enter n, and then if it is C, you can do scanf. So you are taking n, and we don't know how many times the program will run unless we know n. So the number of times hi is getting printed is going to depend upon the value of n. So here, if you will see that as n increases, so if n is 10, it is going to print 10 times. So let's say it is taking 10 unit times. If n is 100, it is going to print it 100 times. So maybe let's say it takes 100 milliseconds and so on. So the number of times or the time depends upon value of n. And this kind of a function, we are going to say run in the time complexity of O of n. Now, I'm going to keep changing this little bit so that we understand when the time complexity is going to be n, when the time complexity is going to be constant, when the time complexity is going to be n squared, and so on. Now, assuming that these two lines I will not write, assuming that you are taking some n from the user. Now, instead of one for loop, if I use two for loops, so if we say the same function we have, and instead of one for loop, let's say we have two for loops. Now, how many times hi will be printed? So the outer for loop of j is going to run from 1 to n. Inner for loop of I is also going to run from 1 to n. So if we want to really analyze it step by step, we can also write it. So my outer is j. When the value of j is 1, how many times the inner for loop going to run? N times. So it is going to print hi n times. Now when j becomes 2, how many times I is going to print? Again n times. So if I give n is equal to 2, how many times total it is going to get printed? So 2n, right? Once when I was 1 and once when I was 2. When j is equal to 3, how many times it will print? Once when I is equal to 1, when I is equal to 2, I is equal to 3. So inner for loop will run 3 times, every time going from 1 to n, 1 to n. So total, our high will be printed 3n. So similarly, if you keep going, when j becomes n, I goes from 1 to 3. Every time for each value, I is running n times, right? So it is going to, when j becomes n, total, it is going to run n square times. So for example, when j is 2, when n is equal to 2, high will be printed 4 times, and so on. So if we have two for loops and both will go from 1 to n, so my time complexity is big O of n square. So very easy, we can directly look from the for loops as long as both are going from 0 to n minus 1 or 1 to n, then in that case, the time complexity will be n square, because whatever is here, I'm just writing a simple high. It might be comparison, it might be checking things or doing some complex calculation, but everything is going to happen n square times. So the time complexity, if you see two for loops, one inside another, will be n square. Now we'll take little different examples. So let's say we have a for loop, but now it goes from I1 to I square less than equal to n. I. Now, what will be the time complexity of this function? So if we have to find out that in this cases, we have to find how many times the word high is printed. That is my uh, time complexity with respect to n. Okay. So let's assume some value of n. So suppose n is 10. So how this for loop is going to run? So for example, first value I is equal to 1. Then it is going to check is I square less than n. So n is 10. If so, you increment. So I square, when I is 1, I square is equal to 1. So 1 is less than 10, it will print high once. Then I becomes 2. It is going to check is I square less than equal to n. So it is going to check 2 square, which is 4, is 4 less than 10. Yes, then we increment, we print high. I plus plus means I gets incremented by 1. So next time I increments by 1, I becomes 3. We are going to check is 9, because this has to be I square. Is 9 less than equal to 10? If yes, we are going to increment and we are going to print high. Then I becomes 4, 16. Then it checks is 16 less than equal to 10? No. So we are not going to increment, we are not going to print high. So for value of n, which is 10, high gets printed 3 times. So can you find what is the correlation between n and this algorithm? Sorry. It's not really log. So what is log of? This log of 8 will also be 3. But it is not actually, we will go through the case of log as well, when it will do a log. But here it is little different than log. Yes, it is square root. That's correct. Because we are checking the value with I square. So the steps are not 1, 1, 1. So if it is not going from 1 to 10, but it is going to a number of times, which is the square root of n. So for example, if I take n is equal to 16, my this value, this condition will get satisfied and we'll do I plus plus and we will print high. So if my n is 16, my high gets printed 4 times. Similarly, if we check when n becomes 25, high will be printed 5 times. So whatever is my n, the high value is going to get printed the root of n times. So here the time complexity we are going to give is big O of root n. So whatever value of n is, we are going to have the square root of that. So this is obviously 2. So we don't have to write. Now when we are going to have log, we will see that we will also see that example soon. But let's first see some more examples where we might end up using the summation series that we saw in the last class. So we saw summation series, then we saw the square series, then we saw the cube series. So I wanted to also give you some examples when that might be useful when we are calculating the time complexity. So if you look at some examples like this, so let's now assume that we have here three for loops. So let's assume one for loop goes okay. Now before going to this, let's think that what if all these values are n? So let's say we have a for loop and where we have three for loops I, j, k, and inside that we are printing, let's say high. Then how many times high will get printed? The first for loop goes from 1 to n, second goes from 1 to n, third goes from 1 to n. So when I is 1, how many times j is going to run? N times. How many times k is going to run? So when j is 1, it is going to run n times. When j will become 2, it will run twice n times. When j becomes 3, thrice n. So it will n square. It will run n square times. Now when I becomes 2, again j will run twice n times and k will run again 2 n square. So similarly, if we get to a point where I becomes n, that time j will run n square times, that time k will run n cube times, right? So if we have some statements inside three for loops, and every for loop is going from 1 to n, then that statement gets executed n cube number of times. So the time complexity of this code is big O of n cube. So whatever is my value of n, if every loop is going to get multiplied by n, so the total number of times these statements are going to get executed will be in terms of n cube. Now I'm going to change it a little bit. So let's say now, can I copy this? So now let's say instead of, okay, now I cannot edit. Now, instead of n, we are going to change the inner values a little bit. So the three for loops will be similar to what we saw, but the range will change. So the first is as it is, it grows up to n. But for the second for loop, it doesn't go up to n. It is limited by the value of I. So j goes up to the current I, and then we are going to increment it by 1. So every time the increment value is by 1. And we are also going to have k, but that k is limited by value 100. K plus plus. And now if you say printf, now we have to calculate the time complexity of this particular code. Now, if you notice, the outer for loop is still going from 1 to n. Now, inner is limited by the value of I. So what do we mean by that? So for the first time when I is 1, it is going to execute 1 times. When I becomes 2, it executes 2 times. When I is 3 and so on. So it is limited by I and not n. While the third is kind of fixed. So every time the third for loop runs 100 times. Now, how do we possibly calculate the time complexity? Sometimes when it is going from 1 to n, it is quite obvious. If you have one for loop, you can say the time complexity is big O of n. If you have two for loops, 1 to n, you can say big O of n square. If you have three, big O of n cube. But if they are not going from 1 to n, then we have to calculate it. So here again, step by step, we have to consider what happens when the value of I is 1, how many times the inner for loops are running. So now let's assume what happens when I is equal to 1. How many times the j will execute? Once. How many times k is going to execute? 100. Okay. Now I becomes 2. How many times j is going to execute? 2 times. So for every time, so when, for example, here there are two, when j is 1, it is going to print high 100 times. Then j is going to increment, become 2. Again, high is going to get printed 100 times. So together, if we notice, the value or the word high will get printed 200 times, right? So first for 1, when j was 1, second time when j was 2. So 100 plus 100, 200 times the inner or this statement gets printed. Now our outer loop is still going to go till n. So next time it is going to increment, it is going to become 3. So what will happen to j? Again, the value is limited by whatever is the current value of I. So j also executes 3 times. Now, every time it executes, it's going to print high 100 times. So if it is executing 3 times, how many times a high will be printed? 300 times. Okay, so on and so forth. When I becomes n, what will be the value j will take? Whatever is the value of I, n. And what is the value of how many times high will be printed at that time? 100 multiplied by n, right? So now what we have to do is, this is my outer loop. So the actual high is going to get printed this value when I was 1 plus when I was 2 plus when I was 3 plus up to 100 multiplied by n. Now this value we have to calculate. That is going to give us the time complexity in terms of n. So let's calculate it here. 100 for I value of 1 plus 200 plus 300 plus up to n multiplied by 100. Now, which series can we use in this case? So there is no such series as 100, 200, 300, but we can take 100 common. So we will take 100 common, and inside you will realize it is a summation series. 1 plus 2 plus 3 up to n. Now we know the formula for this series, right? 1 plus 2 plus 3 plus 4 up to n. What is this formula of summation series? If I goes from 1 to n, and if we are adding I up to n, then that is n multiplied by n plus 1 divided by 2. So we are going to use the same formula, 100 multiplied by n plus 1 divided by 2. Now let's continue it on the next page. So 100 we took common, and we use the formula for summation series, n plus 1 divided by. So this 2 and 100 we will get 50 multiplied by n plus 1. So when we solve this, we get 50 n square plus 50 n. So you will notice that although there were 3 for loops, since the third for loop was independent of n. So if you notice the third for loop that we were talking about, it goes from 1 to 100. So whatever value of n is, it doesn't really affect the third for loop. So basically, the main contributors of time complexity are these 2 for loops. So this for loop is obviously going from 1 to n, but also this for loop, what it is giving us is a summation series. So 1 second time 2 plus 3 plus 4 plus 5. So this is also going to generate and something in terms of n square. Okay. So we are going to see some rules that when we have some terms which are in terms of n and then lower orders, then n square has a much higher say than n. So if I have lower terms, then what do we do is when calculating time complexity, we drop the lower terms and we also drop the constants. Right? So we will look for there are 3 rules to come up with the time complexity. So if this is my exact running time, we are going to drop the constants. We are going to drop all the lower terms in n. So that will give me the time complexity in terms of n squared. Because n doesn't contribute as much as n squared. Similarly, the constant values, initially you will see that their contribution is more, but as n grows, as n becomes millions, then these constant values also do not have much say. And we are going to see the rules shortly, but let's finish a few more examples of this type and then we'll go back that part. Okay. This is clear. So sometimes it might not be straightforward. As I said, if it goes from 1 to n, it is straightforward. You can directly come up with the time complexity. If every loop is not going till n, or it is not incremented by 1, then also it's a different story, right? Then if it is going from 1 to n, but it is incremented by 2 or incremented by 4, then this loop is not going to run n times. Then you cannot say the time complexity is big O of n. Then we have to calculate it in this way, step by step, what will be the value for outer loop 1, 2, up to n. And then you can maybe use some series and come up with the answer. Another trick is again to notice that the third for loop is independent of n. Only the first 2 for loops are dependent on the value of n. So hence the time complexity is n square. But you don't arrive at such conclusions. Once you solve 50 problems, you will realize the patterns and then you will start drawing conclusion. But first at this level, just try to do it step by step. Now, let's take another example of 3 loops. So if we have Let's take 2 for now. Okay. Now here, if you look at the, it should be, yes. So the increment is not happening at rate 1, but it is happening at rate 2. Okay. So in this case, what will be, I think it was, if it is plus, then it is a, okay, that is a different formula. Okay. So now how are we going to calculate the time complexity? Again, we are going to check for each because it is not a straightforward. It's not going 1 to n, step size is 1, 1 to n, step size is 1, then it will be big O of n square. Right now, let's check what happens to different values. So when I becomes 1, how many times inner J loop will run? It goes up to n by 2, n by 2. Next time, value of I is going to be 3. How many times this is going to run? N by 2 times. Again, for every value of I, it is going to run 1 to n by 2. So this is again going to, so this will run 3 times n by 2. Then I becomes 5, it will run 5 times n by 2, and so on. So every time it increases to 2, at some point I will become maybe n, and then it will, let's say it runs n multiplied by n by 2. So what can we say about outer loop? How many times it is going to execute if my step size is 2? So let's assume, let's take some value of n. Let's say n is 100. How many times outer for loop will execute? 50, right? So here outer for loop is getting executed n by 2 times. How about inner for loop? That is also getting executed n by 2 times. So if we try to find the time complexity of this, so this is going to be n squared by 4. Again, the first rule is to drop all the constants because they don't really contribute in the growth rate much. So the time complexity is still in terms of n cube. So this is going from 1 to n by step size 2, meaning this is also going n by 2 times, and the inner for loop is also going n by 2 times. So it is still going n square times. So n square divided by 4, but we are going to see the rule where we actually drop all the constants. So here the constant is 1 by 4 n square. So we are going to drop this. And the time complexity is in terms of n square. So n is n, and what power n has, that's the most important thing while finding the time complexity. So all the constants that are multiplied by n, n square, n cube, or all the constants which are added by are neglected. So we are going to see why it is so. Then one last example we'll see, and then we will discuss the rules. So now let's say we have a for loop again. So now the step size is multiplied by 2. So every time I gets multiplied by 2. So it is not now, the increment is not happening in terms of addition, but in terms of multiplication. So my very first value of I, since the initialization is at 1, is going to be 1. Now when I is 1, j is going to go from 1 to n. So the inner for loop runs n times. So here there are only two for loops. What happens when I is equal to the next time? What will be value of I? It will be 2. 1 multiplied by 2. So it will be 2. Again, how many times j will execute? N times, again n times. So 2 n times. The 2 n times I will be printed and this will be executed. What will be the value of I next time? It is going to get multiplied by 2. So next time the value is going to be 4 and j executes 4. And next time the value is going to be 8 and j, it will be printed 8n times. So now let's assume some value of n. Let's say my n is equal to 16. So I becomes next time 16 and value of j goes to 16n. So how many times total my first for loop is getting executed? So 5 times. Do you see the correlation between this 16 and how the step size is increasing? So every time it is multiplied by 2. So how can we define in terms of time complexity? Yes, this is log. Now this is going to be log base, whatever value is. Now if I, uh, because every time it is going to get incremented by 2. So this for loop actually executes log n times. So whatever is my n, it will execute log n times, where obviously when we don't write any base, it is log 2. What will happen if we are incrementing it 3 times? It is going to be only the base is going to change. Okay, so the base will be 3 and the rest of the things is same. How about inner loop? Is simple, it's going to run n times. So we can say the time complexity of this algorithm is n log n, and depending upon the increment size, that will be my base. So in this case, it is, let's say, 3. Okay. So this is when it will have log n. So it really depends upon how many times these for loops are getting executed, and then that how it affects while we are calculating the time complexity. Now we are going to go through the important rules. Why? So this is how, let's say this is our way of calculating running time. So sometimes we will calculate it little differently. So in this, let's say this was my time complexity. So how do we draw the constants and the lower order terms? So there are 3 rules how we calculate time complexity. I think these are some more examples you can. So this is a very good example they have given, although it is a very big number. So this is kind of, you can say, explanation of why we can drop constant factors and lower order terms. So here maybe a statement they are making is the growth rate of a function is not affected by whatever are constants which are multiplying your n terms and whatever are the lower order terms. So it doesn't get affected that much. So they have given two very good examples. So let's say they are saying we have one time complexity which is 10 square n plus 10 raised to 5. Okay. Now they are saying that this is a linear function. So you don't have to write it as 10 square n plus 10 raised to 5. Linear function is you can directly write it as big O of n. So what happens to this 10 square? What happens to this 10 raised to 5? So if you look at this particular function, this value which is not multiplied by n, we are going to call it as a constant factor. So this is just a constant value which gets added every time. So this value is big enough. So initially it is going to affect. And then this is a constant term which is getting actually multiplied by n. Okay. So both the constant factors we can get rid of. That's what they are saying in the first. So why? So what they have done is, so this 1e plus 10, 1e plus 2, this is nothing but 10 raised to 0, 10 raised to 2. So you look at it, the input size, how it is growing, 10 raised to 6, so 1 million, 10 raised to 8, 10 raised to 10. Similarly, this is a time plotted in 10 raised to 0, 10 raised to 2. So e plus 2 is raised to according to 10. Okay. 10 raised to 14, 10 raised to 16. Now, the dark lines are our usual linear function. So if you look at this green line is the function which is actually a linear function which is dependent on the constant time. So how do you know it is linear? You will see that at 10 raised to 2 input, you are getting 10 raised to 2 in terms of time. At 10 raised to 4 in terms of input size, you are having 10 raised to 4 in terms of time. At 10 raised to 6, you are requiring same amount of time, 10 raised to 6. If my input size is 10 raised to 8, I am requiring time also in terms of 10 raised to 8. If my input size is 10 raised to 10, my time also is in terms of 10 raised to 10. So this is a standard linear function. So it might be something like using one for loop we are showing for I goes from 1 to n and we are printing high. So if we are printing high 100 times, maybe it will take 100 units. If we are printing it million times, it is going to take million units and so on. So this is a linear function. Now what is happening for this function? So for this function, the constant factor is almost 10,000, right? And then we also have this 10 square term. So when we start with my input size 1, if my n is equal to 1, what is this value? 100 plus 10,000. So when n is equal to 1, right? So something 10,100. Okay, so my starting point is here. Do you get it? Why we are getting this? So at n is equal to 1. So what happens when n becomes 100? So when n becomes 100, my first term is 100 multiplied by 100, something again in terms of 10 raised to 5 plus 10 raised to 5. So this is now, you will see that for n is equal to 1, it was a huge difference between this input and this input because of the constant terms. But now once my n becomes 100, here, let's say it was 100 and here it was 20,000 something. So you will see that still there is a little gap between the value of my linear function to value of this function, which has some constant terms. What happens when it becomes 10 raised to 4? So n becomes 1000, then you will see that the difference between these two lines becomes less and less. Because now since n is become 1000, it will be something in terms of thousands for my n. This function, since it has constant, obviously it is going to be higher than my n. Now what happens at 10 when the input size n becomes 10 raised to 6? You will see that now this is the time taken. So after this point, you will see that the growth rate of these two lines is same. Okay. So how are we measuring algorithm efficiency? By the growth rate of that line. So if we have constant factors which are either multiplying or either getting added, there will be some n after which it doesn't matter. Whatever constant we have, whatever big the constant is, whatever big the constant multiplier is, after some time, what is going to happen is the growth rate of linear is going to be same as the growth rate of this function, because you said, see, the constant is 10 raised to 5. So once it passed over that value, though the growth rate almost looks parallelly. So these two lines are growing parallelly. Okay. So in my algorithm efficiency wise, it doesn't make any difference for me. So that's why the claim here is we can get rid of constant factors and we can also get rid of lower order terms. Now let's see lower order terms. So the second example they have given is about lower order terms. So let's have a look at the second example now. Again, it has 10 raised to 5, so bigger constant factor that is multiplying, and so they are saying this is same as a growth rate is linear function. Now 10 raised to 8 n. And this second function is specified by the red lines because it is n square. This red line is a quadratic line. So this is a line of n square. This was a line of linear. So this is my original line. So in this case, what is happening? If my input size is, let's say 10, my output size is going to be 100. So you will see that if my input is 10, my output is 10 raised to 2. If my input is 10 raised to 2, my output is going to be 10 raised to 4. If my input is 10 raised to 4, my output is going to be, output meaning time, 10 raised to 8. If input is 10 raised to 6, my time is 10 raised to 12. So that's how my standard quadratic function time will be. So whatever is power of n, my output will grow square of that value. So if it is 10, it is going to be 10 square, 10 square, 10 raised to 4, and so on. So this is a standard quadratic function they have shown with the red line. The red line. Yes.
For 10 raised to 4, why is the output 10 raised to 8? It should be 10 raised to 16 if it's squaring 4.
No. So 10 raised to, it is n square, right?
Yeah.
So we are, it is going to raise in terms of 10 square of that.
Yeah, so that's 16.
16 10 raised to, yes, actually. So if we are talking about 10 raised to 6,
It should be 37.
yes. So I will,
That's a linear.
But the exponents just double, right? I think that's what.
so if you take the value, let's say about what is value of, so if you take the value of 10 as,
I got it.
so what we're saying,
So the answer is that if it's 10 raised to 4, and if we square it, so it's 10 raised to 8.
yes.
Yeah,
Wait,
the value
so
is where that is.
This is, yes,
Yeah.
so this is the value of n actually. N is 10 raised to 4. So where we are going to find the n square, that is going to be 10 raised to 8. So this is going to be the normal quadratic line, and they have plotted the one with 10 raised to 5 n square plus 10 raised to 8 n. So it is something somewhere here. So for y value 1, then when it is 10, the value is again much higher than the red line because of these two 10 raised to 5 and 10 raised to 8 factors. But again, you will notice that after a point, maybe after this particular point, when it reaches to 10 raised to 5, which is the factor here, both lines will go parallel. So what does that tell us is that this lower order terms, which is in terms of n, has a very less contribution if you compare it with respect to n square. Because if you look at n is equal to 100, what value we are getting by n square? We are getting 10,000. So if we are adding 100 to 8 or not, this n value doesn't affect that much. So after when our n gets too high, let's say after a million, again, those constant values don't matter. So another suggestion is whenever we are calculating time complexity, we can get rid of lower order terms. We can get rid of constants, constant factor. So for this, again, we are only going to focus that it is going to grow in terms of big O of n square. So the time complexity is big O of n square. So those are the rules. So this, I think we already did these examples. So let me give you for activity today, let me give you some other examples of calculating time complexity. So